This is a lecture series on the topic entitled Solid Angle. This is the first lecture of the series. Solid angle is a tool in physics. It has many important applications as well as uses. The concept of solid angle is used frequently in several deductions. The concept of solid angle is used to obtain various laws, various theorems, as for example the Gauss law of gravitation, Gauss law of electrostatics. Solid angle refers to the field of view, that is, how much of an object one can view from a point. As for example, how much of moon is visible from Earth, or say how much of a sphere is visible from a point within the sphere, say from center, or from a point located outside. Before moving to solid angle, let us recapitulate the essentials regarding what we call normal angle or plane angle, that we generally refer to as simply angle. Angle is a supplementary quantity. It is not a fundamental quantity or derived quantity. Consider a line OA and this is another line, call it OX. Obviously, these two lines OA and OX are inclined to each other, or in other words, angularly separated from each other by the quantity theta, which we define as angle. So, inclination between two lines OA and OX is theta, which is angle AOX. To get a measure of theta, let us draw an arc of radius OA. And this is the arc, call it arc AB, so that OA is radius R and OB is also radius R. So, OA equal to OB equal to radius R. Let this arc have length L, say. So, arc length is L, which is arc AB. By definition of angle, theta is arc by radius, that is L by R. Let us mention that theta is angle AOB, or equivalently the angle AOX. Let us call the point O as the vertex point. Let us now switch over to an elemental description of angle. Take derivative of the relation theta equal to L by R, where R is constant fixed. So d theta is dL by R. Let us show the elemental description through a diagram. This is OA, this is OX, and this is the arc we talked about, arc AB. This is angle theta. OA is R, OB is R. This arc is of length L. Let us draw this line from O and another line at a very small, in fact infinitesimally small, angular separation. In other words, we focus our attention to this arc, an infinitesimal arc length, which is an infinitesimal portion of the arc AB. Call this infinitesimal arc portion dL that subtends an infinitesimal angle d theta. This length is R. This length is also R. Let us denote the infinitesimal arc as arc PQ. Let us write these down neatly. D theta is the elemental angle POQ. dL is the elemental arc length arc PQ. We now address a question. Find the angle made by a closed curve C at an internal point O. The answer: let this be the closed curve of any shape that is arbitrary in shape lying on a plane, and we call it C. Consider an internal point, say O. Take any point on the contour, say A. Join OA. Here is another infinitely close point B. join O to B, an infinitesimal angle d theta is generated, and clearly d theta is the angle AOB. AB being an arbitrary portion of the closed curve C. Construct a circle of radius r, and this is how we perform the construction. Call this point P and let this point be Q. So the infinitesimally small arc length is PQ. Now OP equal to OQ equal to R, the radius of the drawn circle. In other words, this OP is R and this OQ is R2. D theta is the angle AOB, which is angle POQ. Same angle d theta is made by the curvy portion AB and circular arc PQ. This is the figure we are referring to, and we mentioned that AB is a small portion of the closed curve C and PQ is a small portion of the circle we have just constructed. So AB is of arbitrary shape and PQ is of circular shape. Now by definition of an angle, d theta is given by the ratio of arc to radius, that is, it is equal to arc PQ divided by radius OP, which is thus dl divided by r. Total angle created by the closed curve C at O is, say, theta, equal to closed integration over C d theta. That is closed integration over C dl by r, which is equal to, let us pull out r outside the integration as r is a constant, and we have 1 by r closed integration over dl. Now dl is arc PQ, which is a portion of the circle of radius r, and so this integration is 2 pi r. R and r cancel out to give theta equal to 2 pi radian. The angle around a point is thus 2 pi radian, and this is it. Angle is dimensionless. Let us do a check. Theta equal to L by R. L is length, R is also length. So length by length is dimensionless. It is m to the power 0, L to the power 0, T to the power 0. M for mass, L for length, T for time. No dimension. The unit of angle theta is radian, denoted by the symbol C. Another unit is degree, denoted by the symbol of a circle. The relation between them is 2 pi radian equal to 360 degrees. This implies pi radian equal to 180 degrees. This means 1 radian equal to 180 degrees divided by pi, which on evaluation gives 57.2958 degrees. Let us show the angle 1 radian through a diagram. Consider a line of length, say r, and an arc also of same arc length r, and let us join the endpoints by a line which is also of length r. So r is the radius, and L equal to R means that arc length equal to radius. Under this situation, the angle created here is theta and is identified as 1 radian. So theta is L by R, which is equal to R by R equal to 1 radian. This shows what we mean by 1 radian. 1 degree equal to 60 minutes, 1 minute equal to 60 seconds. Consider a point O. Let us draw a line and another line here from the same point O. So this is line OA and this is line OB. This is the arc AB. We draw 2 more arcs, call them A prime B prime and A double prime B double prime. This is angle theta. Theta equal to arc AB by radius OA. This is same as the ratio arc A prime B prime divided by radius OA prime. This is again equal to arc A double prime B double prime by OA double prime. Clearly, length of arms OA OB has no effect on angle theta. Why? This is because extension or reduction of lengths OA OB does not change inclination. So theta does not change. A quick recap. This picture shows that OA and OB are inclined obliquely. For theta equal to 0, OA and OB are collinear and lie in identically the same direction and sense. For theta equal to pi by 2, OA and OB are orthogonal or perpendicular. For theta equal to pi, OA and OB are collinear but lie with their endpoints in opposite direction and sense. Angle occurs in a plane. It is two-dimensional. To define orientation between two lines, we need one coordinate, one angular coordinate, say theta. And theta equal to 0 on a line OX in 1D. So the concept of angle is not a feature or characteristic of one dimension. It does not make sense in one dimension. A question: how many radii are included in a half circle in a full circle? The answer: consider a half circle and let us draw it. This is the center O. This endpoint is A. Radius is R. Let us mark this point as B such that arc length AB is same as the radius R. Join OB, which is R, the radius. So this angle AOB is 1 radian. Let us mark this point as C such that arc length BC is same as the radius R. Join OC, which is R, the radius. So this angle BOC is 1 radian. Let us mark this point as D such that arc length CD is same as the radius R. Join OD, which is R, the radius. So the angle COD is 1 radian. This endpoint is, say, E, and this angle is pi radian. Angle AOE is 3 radian plus a bit more, that is plus some more radians. Actually, angle AOE equal to pi radians, which is nearly equal to 3.14 radians. Hence, circumference of half circle captures a little more than 3 radii, that is little more than AB plus BC plus CD, that is R plus R plus R. Actually, it is pi equal to 3.14 radii. And a full circle is 2 half circles equal to 2 pi radians, that is 2 into 3.14 radians equal to 6.28 radians. Hence, circumference of full circle captures 6.28 radii, that is a little more than 6 radii. Let us furnish alternate description of angle through trigonometric relation. This is line OA and this is line OB. Drop a perpendicular and call this point P. The foot is Q. This is obviously 90 degrees. This angle AOB is theta. Tan theta equal to perpendicular by base. So it is equal to PQ by OQ. To create an angle, we need to join the endpoints AB of a curve to a point, say O. Suppose this is the curve AB. Join the endpoints AB to point O. This angle is theta. Alternatively, we can join all the points between the endpoints AB lying on the curve to the point O. And this is how we do it to generate the same angle theta. Note: a surface has a contour or border, I mean an open surface. What if we join the points of the contour to a point O? This we will discuss in lecture 2.